Francis, and her title is Graded Linearisations for Linear Algebraic Group Actions. So many thanks. Many thanks to the organisers for the invitation to speak at this meeting. It's a pleasure and a privilege. Some apologies. So first of all, for a rather uninformative title, I'll try and explain a bit more in a minute, and also for the fact that when I started thinking about what I would talk about here, I completely forgot that this was supposed to be a meeting about symplectic geometry. So this is mainly going to be a talk about algebraic geometry. There will be some symplectic geometry and moment maps and things related to moment maps at the end, if I get there, which I hope I will. But I'm afraid the written version has absolutely no symplectic geometry in it at all, so apologies for that. So what I want to tell you about is an extension of geometric invariant theory. It goes back to the 1960s, Mumford's geometric invariant theory to linear algebraic group actions which are not necessarily reductive, and some applications and potential applications of that. So it's based on joint work with lots of people, including Greg, Brent, Vicky, Josh. I also should have listed my former student Tom Hawes, who definitely should have been on that list. So geometric invariant theory and relations to moment maps, I've learnt lots from over the decades about it from Simon himself, from students of Simon's and their students as well. So in particular Michael Thaddeus, who can't be here this week unfortunately, from Sean Martin, who was here earlier. I'm not sure whether he's still here today, both of whose names will appear later in the talk, and others, of course, Richard Thomas and Julius Ross and lots of others. So many thanks to all of them, and particularly to Simon, who inspired them and inspired me. So yes, a bit of background. So I'm going to be talking about moduli spaces in algebraic geometry rather than more symplectic geometry point of view, and they're often constructed as quotients of algebraic varieties by linear algebraic group actions. And just as a reminder, so a linear algebraic group, I'll work over the complex numbers today. So then it's a semi-direct product of a unipotent group, which is a normal unipotent group, which is its unipotent radical, by a reductive group. And lots of the sorts of moduli spaces that and moduli problems which appear and are studied are actually the groups are reductive, and that means that Mumford's geometric invariant theory, which I'll remind you a bit more about in a minute, can be used, and also symplectic geometry can be used to construct them and study them. But I want to talk about extending this to groups that are not necessarily reductive. So a simple example is at bottom here, the automorphism group of a weighted projective plane with weights 1, 1 and 2. So its automorphism group is not reductive, but its unipotent radical is 3 copies of the additive group of the complex numbers. And then there's the reductive part, which is essentially GL2 acting on the weight space with weight 1. So that's an example. So these sorts of non-reductive groups do come up in moduli problems. but what I really want to concentrate on is actually the way that non-reductive groups come up in sort of classical moduli problems, which originally, which are thought of in terms of reductive group actions, such as moduli spaces of stable curves, so mg bar, so in these moduli problems, typically we have to impose some sort of stability condition to get a nicely behaved moduli space, and so it would also be nice to be able to construct moduli spaces of unstable objects for these sorts of moduli problems. So if you want to think about trying to study the whole moduli stack, which includes all complex projective curves, sort of including very nasty singular ones, then one way that you might like to try and do that is to try and in some sense, some way stratify this moduli stack, so divide it up into pieces so that the moduli space of stable curves would be a nicely behaved sort of open piece, but then the other pieces, if you stratify appropriately, would have their own moduli spaces associated to them, and then you could try and study those moduli spaces and also study how they link together. So the mg bar, the moduli space of stable curves of genus G, and then you can add mark points. You can also look at stable maps to a projective variety. So these are all examples of moduli spaces that can be constructed using classical geometric invariant theory by reductive groups, so essentially special linear groups. So mg bar, you can construct a group action on a Hilbert scheme, or you look at sufficiently high powers of a canonical bundle, so you look at canonically embedded curves, and you get a GIT quotient out of it, which turns out to be mg bar. So can we somehow use this GIT picture to construct moduli spaces of unstable curves? So people have obviously looked at singular curves for a long time, and there's a nice description going back to Sayre and Rosalik, I think, in the 1950s. And there's a description, as you would expect, in terms of the normalization of the curve. And I'm not going to talk about the details here, but you can describe singular curves in terms of the normalization, and then some extra data which describes the singularities for you. So back in the 1960s, Sherwood-Eby used this construction in the unibranch case, so the case when, as sort of cusps and things, if the normalization map is actually bijective, that's a relatively simple setup, and Sherwood-Eby used this Sayre-Rosenlink construction to try and find a classification of unibranch singularities, or curves with unibranch singularities. And effectively what he was wanting to do was to construct quotient by a non-reductive linear algebraic group. But classical GIT had just been developed, but there wasn't a nice quotient construction for non-reductive groups at the time, and so he did it by looking for slices for the action of these groups, and described a sort of classification for the unibranch case in this way, and in particular showed that there are a non-trivial moduli for the singularities. So the groups that he was using have been come up in all sorts of different areas, in particular used by Demai and others studying jet differentials. So it's just the reparameterization group, a bundle of k-jets of holomorphic curves. So you can think of it as a group of matrices, and it's an upper triangular group. So its unipotent radical is the strictly upper triangular part, and then it's the semi-direct product of that by a copy of the multiplicative group, the diagonals. So what's going on here is that you've got essentially free parameters along the top row, except the first one has got to be non-zero, and then the entries above the diagonal are all polynomials in these particular polynomials in these parameters. So so that's an example. But it's not, so I want to think about the singular curves in a slightly different way. So going back to the construction of the of mg bar, the moduli space of stable curves as a GIT quotient. So I'd like to sort of take that that setup and use that to find discrete invariants of unstable curves, singular curves, with worse singularities than nodes, so that we can try to actually construct nice moduli spaces of these singular curves using GIT methods. And you can try and do the same thing to other classical moduli spaces that are constructed using GIT for reductive groups. So you might be interested in trying to construct moduli spaces of unstable sheaves of fixed Harder-Narrow-Simon type over a fixed projective scheme, say, or indeed moduli spaces of unstable maps from curves to a projective variety. And it turns out that, as I said before, we're led to use non-reductive GIT here rather than classical GIT to get these moduli spaces, even though initially we're starting with a reductive group action. And yes, so typically we can't just hope to use the GIT action as it stands, so we have to be a bit careful and guess answers in advance and then set up the GIT problem.
I mean, presumably one way of thinking of the problem is that you take the upper triangular matrices, which make it difficult, but the lower triangular matrices, if you put them together, you get the general linear group, which is reductive. So if you combine the upper triangular one and the lower triangular, which is sometimes opposites, skillfully, you should be led in the right direction.
So to some extent, yes, and to some extent, no. So it's
Answer.
okay. I will leave it at that and move on rapidly. So the classical geometric invariant theory, where this sort of stratification or the motivation for this stratification comes from, is classical geometric invariant theory, where if you've got, well, this curly K was the Hilbert thing that I was using for mg bar, but if you've got some projective variety, then with a linear group action of a reductive group, then classical GIT tells you how to stratify the variety so that you've got an open subset, which is the stable points. Well, in this particular case, stability is the same as semi-stability. More generally, you'd have the semi-stable points as the open stratum. And then the strata are determined by by how unstable the points are, roughly speaking. So in terms of what maximally destabilizing one parameter subgroups that come up in geometric invariant theory. And it turns out that in this stratification, the unstable strata, sorry, wrong thing. The unstable strata can be defined in terms of certain parabolic subgroup of the reductive group, and I'll talk in more detail about this in a minute. But roughly speaking, if you want to try and construct a nice quotient of an open subset of a particular stratum by the group, then the natural thing to do is to study the action of this parabolic subgroup, which will of course not be reductive itself. So I should say that you can find sort of something that behaves a bit like a quotient for each unstable stratum. So it's a categorical quotient, but it's a very long way from being a nice geometric quotient of the stratum. So in the sheaves case, if you were looking at sheaves of fixed hard and narrow Simon type, then that would only remember for you the associated graded thing. So you're forgetting a lot of information. So if you want to get really nice geometric quotients of these unstable strata, then you're going to have to refine the stratification a bit, and then working with these parabolic subgroups turns out to be the way to go. Yeah.
The stratification you have is given somehow by the intersection of the element of some polytopes that you have when you have polytopes to remember, because polytopes have stratification as well.
So what I should say is, for an audience of symplectic geometers, is that one way to define the stratification is as the Morse stratification for the norm squared of the moment map. So yes, moment maps and things definitely come in here. So I will hopefully come back to that. So now just a brief reminder or tell you roughly about how classical GIT, geometric invariant theory, works. So assume that we've got a complex reductive group acting on a complex projective variety, and there's an extra ingredient that we need, which is a linearisation of the action. So we want an ample line bundle and a lift of the action to the ample line bundle, and we can think of the variety as just sitting embedded in projective space, and the action given by a linear representation of the group. And then a standard sort of algebraic geometry picture to X, or really to X and the ample line bundle, we associate a graded algebra, finitely generated graded algebra, and then we look at the linearization gives us an action of the group on this, and we look at the algebra of invariance. And the crucial thing is that if G is reductive, this algebra of invariance is itself finitely generated as a graded algebra. And so you can look at the associated projective variety, which is our sort of GIT quotient for this setup. And so then if you want to think about what that looks like geometrically, the inclusion of the invariance in will give you a rational map in the other direction, so from X to this GIT quotient. And you can then look at the open subset where this rational map is actually a morphism, so where it's well defined. And so that gives you a surjective G invariant map from the semi-stable points to this this GIT quotient. And one of the really it's not at all obvious but important things is that in this reductive setup that map is surjective. And then but it's not necessarily just giving an ordinary nice geometric quotient, but if you restrict a bit further to the open set of stable points, then you get a nice geometric quotient of the stable points, which is compactified by this this projective variety, which is the GIT quotient. And
Can I ask you
yep.
a basic question? So, for an analyst, the linearization is something maybe different.
Yes.
Would I be thinking of the linearized action if I was acting on a smooth manifold?
So no. So no. So sorry, it's just clash of terminologies here. So in GIT,
the line bundle is not ever the tangent bundle.
no, it's just a line bundle, and so the linear part is that it's turning our action into a linear representation, because the point is it allows us to think of the variety as sitting inside some projective space, and so then we want the action to extend to a linear action on that projective space. So that's the linear bit of it. So it's this linear representation here which is giving us the action. So so yes, so there's close links with representation theory and so on in this setup. So geometrically and topologically, what this projective variety that we get is the so we've got the open subset of our original variety, which is the semi-stable points, quotiented by an equivalence relation, which is sometimes called S-equivalence, such that two semi-stable points are equivalent if and only if the closures of their orbits meet in the semi-stable set. So, so one way round here is obvious. If the closures of the orbits meet in the semi-stable set, then the points must get identified in the quotient, because the map is G invariant and continuous. But in fact, that's an if and only if. And in this reductive setting, so a complex reductive group we can think of as being the complexification of a maximal compact subgroup, and then we can identify the GIT quotient with the symplectic quotient for a suitable moment map, which is determined by the linearization. So, so we find that the inverse image of 0 under the moment map always sits inside the semi-stable set, and the inclusion composed with the surjection from semi-stable set to the GIT quotient induces a homeomorphism between the symplectic quotient and the GIT quotient. So, so that's a very quick review of the setup for GIT. And one of the reasons that it's very, very powerful is that we have these relatively simple criteria, the Hilbert-Mumford criteria, for which points are stable and which points are semi-stable. So we don't have to know what all the G-invariant sections of powers of the line bundle are in order to, which is a very hard problem, in order to know what the stable sets and the semi-stable sets look like. So I'm not going to go through detail how it works, but you first of all look at a maximal torus, and then you have a very simple picture of which points are semi-stable or stable for the maximal torus in terms of looking at convex hulls of weights for the action, and then you have you can once you know what the semi-stable and stable points are for the maximal torus, then that essentially tells you what they are for the whole group. So this is the source of a lot of the power of GIT. So something else that you can do in the classical case is get rid of, well, at least the worst singularities in the sort of the bad setup where you've got strictly semi-stable points. So the really nice case is where you've got stable points and they're all semi-stable, And then on the one hand, your GIT quotient really is a projective variety, because it always is, but also it's actually a geometric quotient of the stable set. So you don't have to worry about whether you have to glue together orbits whose closures meet in the semi-stable set. So that's the best situation if the semi-stable set is the same as the stable set. But in general, as long as you've got some stable points, there's a construction that you can do of a blow-up construction, which enables you to start with the original variety X and do equivariant blow-ups, so that you eventually end up with a new variety X tilde with the property that semi-stability equals stability for that. And so then if you take the GIT quotient of X tilde, then it is it's some sense well, at least a partial desingularization of the original quotient. If X itself is non-singular, then it has at most orbifold singularities. So
How would this look like for bundles?
So so if you would have to blow up the polystable bundles that are not actually stable, and you do that with the maximal dimensional automorphism group first, and then you just repeat the process essentially. So so I want to sort of summarize the reductive picture like this, because this is the part of it that goes over nicely to the non-reductive setup. So we think of the good case as when we've got semi-stability the same as stability, and we want to know that we've got at least some stable points. Otherwise we get an empty quotient, which isn't terribly helpful. And so in that case we get a quotient which is simultaneously projective and a nice well-behaved geometric quotient. And then the more general case, we can think of we've got the geometric quotient of the stable set, and we can compactify it either by looking at this singular thing, the GIT quotient, or from this point of view, I'd prefer to think about it as being compactified by this partial desingularization, because the partial desingularization, the blow-up process, doesn't affect the stable points at all. So, so that's the picture that goes over to at least more or less to the to some non-reductive setups. So, right. So, what are the issues? Why is there a problem with extending classical GIT to the non-reductive setting? So, the first obvious problem is that we get stuck at the first step in the construction that I described, because if we try and look at the projective variety associated to the algebra of invariance, we're in trouble because when G is not reductive, this algebra of invariance is not necessarily a finitely generated as a graded algebra. So we can get some rather nasty scheme, but we certainly don't get a projective variety associated to it. So so what can you do? Well, there's certainly ways of making sense of the stable points, and lots of different people over the years have thought about this in slightly different ways, but there are relations between them. So you can get a nice geometric quotient of a stable set, even if the group is not reductive. But there's not necessarily, in general, a sensible sort of projective completion, or compactification. So you can define something that we call an enveloping quotient for the semi-stable points, but it's not necessarily projective. If the invariants are finitely generated, then it will be projective, but it's not in general projective. And even if the invariants are finitely generated, the morphism you get from the semi-stable points in X to this enveloping quotient is not necessarily onto. The image is not necessarily a variety, so it might be just some sort of constructible subset. So, and another big problem is that the Hilbert-Mumford criteria for stability and semi-stability don't generalize, at least in an obvious way. So what I want to talk about is a situation where things do behave nicely for non-reductive groups. So we want to start off by thinking about so a non-reductive group, it's a semi-direct product of a unipotent group by a reductive group. So to some extent the problem is dealing with the unipotent group, because if we can find a sufficiently nice way to quotient by the unipotent group, then we should have a residual action of the reductive group, and we know how to deal with reductive groups. So we want to concentrate on unipotent groups to start with. And it turns out that it's useful to impose a condition on the unipotent group, which is very typically satisfied. In fact, I don't know of any, all the sort of obvious examples of unipotent groups do. Whoops. There we go. Okay. Whoops. Go back a bit. All the obvious examples of unipotent groups do satisfy this. So we want to think about unipotent groups which are graded in the sense that there's a one-parameter family, a multiplicative group's worth of automorphisms of this unipotent group, such that all the weights of this C-star action, this multiplicative group action on the Lie algebra, are all strictly positive.
For example, weighted predictive spaces at the beginning is exactly what I mean.
Absolutely. And in fact, the automorphism group of any complete toric variety has the structure so that it's there's a central subgroup of its Levy part, its reductive part, which grades the unipotent radical, and parabolic subgroups of reductive groups also have the same property. So we want to look at this situation where we've got we can construct this semi-direct product we call U hat of our unipotent group with a group of a multiplicative group which has this action, conjugation action on the unipotent group with all strictly positive weights. So it turns out that if you've got a linear action of this U hat, so if you're interested in a linear action of the unipotent group which extends to a linear action of this U hat, then first of all you can call it twist the action of U hat by any character. So that just means we multiply the lifted action on the line bundle by a character of the group, and that doesn't affect the original action on the projective variety X, but it changes the linearization and changes the GIT picture a bit. So we can do that. We can twist by any character, and indeed we can twist by a rational character, because GIT is essentially unaffected if you replace the line bundle by a positive tensor power. So we can shift the action by a rational character, And it turns out that if you choose that character appropriately, then GIT for this U hat action is almost as well behaved as in the classical case. So here's the theorem. So yes, I'll draw some diagrams to try and explain what's going on here. So the idea is that we look at the weights for the multiplicative group action. So we're assuming that we've got a linear action of this this U hat on our projective variety with respect to an ample line bundle L, and so that effectively gives us a linear representation of U hat, and we can look at the weights of the multiplicative group action. And twisting by a rational character is basically we're just moving where the origin lies in this picture of weights. We'll have finitely many weights. And so you have in particular the weight, the minimal weight here. And what we want to do is we want to twist by a character so that the origin lies just above the minimal weight. And then provided that we've done that, and provided that we've got another condition, technical condition, but it's basically the analogue of semi-stability equals stability for the unipotent group action, then we get a nice geometric quotient of the stable set, which is the same as the semi-stable set, and it's a projective variety, and we have analogues of the Hilbert-Mumford description. And the stability equals semi-stability condition that we need is this condition star at the top here. So it's basically saying that if you're in the fixed point set for the star action, where the associated weight on the line bundle is this minimal one, then we want to have all such points should have trivial stabilizer in the unipotent group. They'll be fixed by the C star, but we want them to have trivial stabilizer in the unipotent group. And the grading is such that that you'd expect that to happen. So the grading is such that this end, everything will actually be fixed by the unipotent group, but at this end you'd expect things to be effectively moved over by the unipotent group. So so that's the condition which allows you to be in the really nice case. So you've got semi-stability equals stability, you've got a Hilbert-Mumford description of the stable set, which is the same as the semi-stable set, and you've got that the invariants are finitely generated, the GIT quotient is just the projective variety associated to the invariants, and it is just the geometric quotient of the stable set. So that's the really, really nice case. But even without this semi-stability coinciding with stability condition, we can still do an analogue of the blow-up construction, where we can find we can do some blow-ups essentially until we have, well, it might not quite be this condition if the generic stabilizer in X for U is non-trivial, but something close to this condition where we do have a nice geometric quotient. So that's the nice setup. So if we've got our unipotent action which extends to the U hat, and we're prepared to twist the linearization appropriately by a character, and then we have a sort of analogue of classical GIT. And so, in particular, we can apply this to the sort of unstable strata in this setup where we start with a linear, when we start with a reductive group action, because so this is essentially the slide I had before, but in this case the parabolic subgroup that we want to where's the pointer gone? Oops. Oh, sorry. I can't get the pointer to work anymore, but oh yeah, there it is. So the parabolic subgroup is semi-direct product of its unipotent radical by the Levy subgroup, a reductive thing, and it's always the case that there's a central one-parameter subgroup of the Levy which grades the unipotent radical. And so what we can do is we can look at the linear action first of the u hat that we get on and quotient by that, and then we've got residual action of a reductive group, which is just the Levy quotiented by this central C star.
Sorry, just to understand. This is an application of the theory of non-reductive quotients to unstable strata in the ordinary.
Exactly.
GIT.
Yeah. So it's one of the applications of our theorem. So in particular, as I said earlier on, if you're interested in constructing moduli spaces of sheaves of fixed hard and narrow Simon type over a non-singular projective variety, so this is work in progress with Vicky Hoskins, Greg Bertsey, and my student Josh Jackson. So we can set the so there's this beautiful construction due to Simpson, and there are other related constructions, GIT constructions of moduli spaces of semi-stable pure sheaves on this variety for fixed Hilbert polynomial. So it's one of these GIT quotients of by a special linear group, and so Vicky showed that you can, if you're interested in any fixed hard and narrow Simon type, you can set up this construction in such a way that the stratum, so there is one of these strata coming from the stratification that I just showed you, which corresponds exactly to sheaves of fixed hard and narrow Simon type. And so then you can use non-reductive GIT for this parabolic subgroup of the special linear group to construct these, to try and construct moduli spaces of sheaves of fixed hard and narrow Simon type. So, as I said before, you're not going to get you're going to have to refine the stratification from just the hard and narrow Simon type. So to get nice moduli spaces and nice quotients, you'll have to, in particular, split off the things that are polystable, and so you'll have to refine the stratification, but then get nice moduli spaces when you've done that. So that's work in progress. Similarly, so what Josh Jackson is working on and is making very nice progress with is looking at unstable curves of fixed type. So again, you've sort of set up your GIT picture for the moduli space of stable curves in a suitable way, and then you have to sort of guess what properties of what discrete invariants should correspond to the strata, and construct, and then when you've done that, you can use this theory to construct moduli of these things. And this is actually in many ways nicer than the sheaves case, because this condition star, that semi-stability that coincides with stability for the unipotent radical, it's sort of automatically satisfied in this setup, whereas it's certainly not in the sheaves. case. So in the sheaves case, you have to be prepared to worry about blow-ups and so on, but here we don't.
Can I ask, what does it mean fixed type? You have, like, fix the singularity, how many singularities you have, and sort of how they are distributed?
Yeah, so we're thinking about it, going back to this Rosenlich description that that I talked about very briefly right at the beginning, but yes, and the different singularities are sort of separate from each other, and then in some sense like sheaves that are direct sums of summands, and then you have to try and understand the type of the each singularity. Yep. So I promised to mention Michael Fabius's name, and so in particular for variation of GIT in this non-reductive setting. So I will say this very fast, but in this, so we've got extra ingredients. So in the reductive GIT, the ingredient that we've sort of added to get our quotient is just the linearization, the line bundle, and the lift of the action to the line bundle. But in this generalized setup, then what we want to do is we want to have a central one-parameter subgroup of the reductive part of our linear algebraic group, which grades the unipotent radical and defines for us our u hat, and we first quotient by the u hat, and then we quotient by the residual reductive action. So in this situation, we can worry about, first of all, what happens when we vary the linearization, which is essentially exactly as Fabius and others studied in the classical case. And we can also worry about what happens if we vary the central one-parameter subgroup that does the grading for us. And it's enough really to think about the simple case where this condition star is satisfied, because in general we can blow up and then reduce to that case. So just to say very briefly what happens. So we look at the center of the Levy subgroup of our group. We look at the set of weights for this action. So we might have something this. We look at the convex hull of that set of weights, and then we look at the rational, the Lie algebra of the center. So the weights are living essentially in the dual of the Lie algebra, but in the Lie algebra there's a rational open cone corresponding to the central one-parameter subgroups which grade the unipotent radical, and that cone gives you an allowable part of the boundary, consisting of all the boundary points which will give you the minimal weight for some one-parameter subgroup in this cone. And so in order for our theory to tell us that we will have a well-behaved GIT quotient, we have to twist the linearization by a rational character which lies in the inside of this convex polytope, but just inside the allowable boundary. So it turns out that once you've chosen your linearization to twist by, then the GIT quotient is independent of the choice of one-parameter subgroup that you're using. And it turns out that if you move around the interior of this convex polytope just inside the allowable boundary, then you can do that with just finitely many steps, for each of which the central one-parameter subgroup that you're using grading the unipotent radical is fixed. And so when that central one-parameter subgroup is fixed, then varying the line bundle and the linearization behaves just as in the classical case. So we have quite a nice generalization of variation of GIT, which basically boils down to the ideas of Michael Fabius and Dolchev and Hugh. So guess I think I'm going to have to skip over this very fast if I'm going to bring any symplectic geometry in. But we can sort of set up this this picture, and there are two possibilities: that we either have a sort of internal situation where the group that we're interested in quotienting by already has a one-parameter subgroup that does the grading for us, or we might have the situation where we have an external one-parameter subgroup, in which case, if we're really interested in a quotient by the original group H, then we can always add in a copy of P1 and look at the H hat action on X cross P1 and quotient, and look at the quotient. So I don't really have time to talk about that in detail. So this is just the sort of formal setup that you can think of, the sort of extra structure for this sort of generalized GIT picture of a graded linearization, where you've got, as well as your line bundle, you've a linearization, you've also got an extra multiplicative group GM or C star, which is helping you to define your quotient. Okay, so I want to just spend 5 minutes bringing in symplectic geometry and moment maps, or moment map-like maps. So, the theorem about the U hat actions, which I gave you, there are different ways to prove it, but they all, to some extent, come down to really understanding, they're by induction essentially on the dimension of the unipotent group. So they come down to understanding what happens in the very simple case when the group is just the complex numbers under addition, when the unipotent group is that. And so in this situation, if you're acting just on a projective space, then you're in good shape, because you can use Jordan normal form to essentially extend the action of the unipotent group to SL2, and indeed you can essentially extend the action of the U hat to GL2. And in this situation, for an action on a projective space like this, the U invariants are finitely generated. This is Weizenbach's theorem. And moreover, you can relate them to invariance for SL2 in such a way that you end up with, you're able to identify the GIT, the non-reductive GIT quotient, with a GIT quotient of either, well, you can put in a P2 rather than C2 here, if you like. So P2 cross Pn by SL2. And that means that you can really understand, you can use the classical GIT to really understand what's going on here. And so then this picture links in with the construction of Guillemin, Jeffrey and Shamar 15 or, well, 20 years ago really. Now, it was published a bit later than the ideas arose. So this is symplectic implosion. So the ingredients are essentially the same as for symplectic reduction. You've got symplectic manifold Hamiltonian action of a compact, preferably connected group. You've got a moment map, and you look at the positive bar chamber, and instead of taking the inverse image of 0 under the positive bar chamber and quotienting by k to get the symplectic reduction, instead you take the inverse image of a positive bar chamber, you do some collapsing on the boundary, and you find that that gives you a sort of stratified symplectic space, which in some sense, abelianizes the original action in that you've got a residual action of the maximal torus, and you can then quotient by that, so the example that's going to be important or relevant here is the very, very simple example where k is just SU2, and because of, to make it fit with the conventions that I've had earlier, we want to take the positive Weyl chamber to be actually the negative real axis, so sorry about that. And then what we're doing for our symplectic implosion is we're just taking the inverse image of the negative axis under the moment map, and then we're doing some collapsing at the boundary, which is just the origin. And it turns out that you can link up symplectic implosion with these non-reductive GIT quotients using the universal implosion. And so what you end up with is that the symplectic implosion can be identified with the, well, at least in the algebraic case, with the non-reductive quotient of x by a maximal unipotent subgroup of the complexified group. So that was very, very fast, apologies. So in the simple example that we were looking at before, the trick is that if you quotient by, so you take the symplectic implosion to quotient by u, but then you want to quotient by the S1. And so this is, if we assume for simplicity that the S1 is just the maximal torus in SU2, so then we're just saying that the moment map has got to, the torus moment map has got to take some fixed value. And if we ensure that that fixed value is over here, rather than, well, the boundary would be really bad, or over here would give us the empty set. If we ensure that that we're quotienting within the negative axis, then we will get that the quotient by the u hat can be thought of as the inverse image of some sort of moment map for the unipotent, well, for the full u hat, and then the quotienting by maximal compact subgroup given by the circle. So I really don't have time to explain the details, but roughly speaking, you get something in general in the projective setup which isn't a moment map in the usual sense. So it has this sort of more complicated infinitesimal picture. But you can hope that, you can hope that the non-reductive GIT quotient might be the inverse image of 0 under this non-reductive moment map-like map quotiented by a maximal compact subgroup. And it's certainly not always the case, so taking maximal unipotence in a reductive group and symplectic implosion shows you that you have to do much more complicated things in general. But in our nice setup, provided that we're twisting by an appropriate rational character, which in this picture means adding an appropriate central constant to the moment map, and the crucial thing is that we're going just above the minimal weight space, so we're having a good chance of being in the negative half line. Then we can actually get this nice picture of our non-reductive GIT quotient being given by the inverse image of 0 under some sort of moment map-like thing quotiented by maximal compact. So I have got to the final slide. Oh, so that was under the assumption that we had the the semi-stability coincides with stability condition, but you can still say something more generally. And so this moment map picture really is useful from an algebraic geometry point of view if you want to do things like calculating Betti numbers and generators for cohomology rings and intersection pairings on these non-reductive GIT quotients. So using in particular ideas that Sean Martin came up with a couple of decades ago, I guess, or a decade, I can't remember when. So I'm sorry to have overrun, and happy birthday, Simon.
So I have a comment on the questions. I was intrigued by this one parameter subgroup.
Right.
Because in the in Kähler geometry, we're studying extremal metrics. One gets a kind of a preferred one parameter subgroup.
Right.
I wondered if there was some.
So, I mean, that is, I don't know nearly as much as I should do about
I can help you out if you want on that one.
Go on then, go on then.
Well, first of all, I should say, I think you're going to be a marvellous example of how to present a very complicated subject and make it look easy. And nobody should underestimate, the technical difficulties and the skill with which Francis has not ignored them, but showed you how somehow you can still understand what's going on. So that's the general remark about the whole lecture. On this last issue, I think I have several things that could be said which would hopefully enlighten different people. This one parameter subgroup will be absolutely crucial, and it's very difficult to know what it is and where it comes from. In different contexts, it comes from different things. Let's start at the far end. If you go back to the Harlan and Simon paper, where they were thinking of the Balkan, it comes from the Frobenius automorphism. Bottom line, we're doing it comes from a Morse flow. If you go to the Lie group case situation, what it is the parameter, if you introduce a circle which is an extra variable, it's like going from SUN to UN. You put in the central term. The other groups not very so obvious. That is always about extra parameter which you can interpret for a flow, number theory-wise, geometrically. It is the universal trick. And another point of view is that you can think a lot of this theory was generalized by people, friends of ours, from the case where you have things which are Lie algebra, which is the Lie group, moment maps in particular. Bots this with various people. And then, of course, it's much technically different. The Lie group and Lie algebra are approximately the same, near the identity by the exponential map. But of course, they're not. As soon as you get far away, you get into quite serious difficulties. Now, when you create the moment map with values in the Lie group, you have to call it something different. You call it the group management. And then the one parameter now is the scale of the Lie group. If it's a semi-simple group, it's just one parameter. This is the scale size. And what physicists call the large volume limit and so on, is to do with that scale size. That parameter is the universal parameter that is running around all these stories, wearing different hats in each place. So I think that partially answers Simon's question. And in the Kähler case, it's actually the parameter that leads the positive Kähler cone to the negative Kähler cone. In the more general case of Seiberg-Witten theory, you have a number of candidates, and it's the parameter that links them all together. So it is a universal parameter that appears in all these theories under different guises, and it is essentially the heart of all these problems. But it has different names in different subjects. And it is really, the more you look at it, the more and it actually starts off in many situations not being an invertible thing, it's semi-invertible. The Frobenius is semi-invertible, it's endomorphism. But then you somehow skillfully manage to, like your map was only a surjection, and you have to somehow turn it into something more respectable. All the difficulties will still arise there in the same way. Sorry to go on long, but I thought it might be a helpful comment. Different members of the audience have different interests. There are physicists, differential geometers, and few number theories, algebraic geometers. Each one, this will have a different meaning.
Absolutely, and yes, so I certainly recognise some of the things that you were saying there, in particular the going from SUN to UN.
Yes.
So the simple example, which is the sort of heart of how you prove the things, it is very much going from SU2
Should add one other
to
thing.
U2.
When you go from the group to the loop group, that's adding another circle, and that corresponds going to replacing the Lie algebra by Lie group. So the Lie group, as opposed to the algebra, tells you where the circle comes on in a rather natural way. It's the extra circle in a loop. As people know, that why do loop groups look like a group of one higher rank? Because they have that extra circle, which is the rotation of the string.
Are there more questions? I actually have two. This is geometry me and algebra me. So geometry me, so in Kenji's talk, there was this symplectic implosion applied to, which I'm sure goes back to the framed flat connections.
Right.
So what is the quotient actually algebra geometrically?
So
So he used this to sort of make something that's couple dimension up from the usual modular space of flat connections and non-singular.
So I think you were using symplectic cuts, and yes. So I think the symplectic cuts do link with this blow up procedure, but there's some subtlety around. So in the reductive case, if you're faced with a bad situation where semi-stability is not the same as stability, then there are potentially two things that you can do. So certainly if your group is abelian, if you've just got a torus, then you've got lots of flexibility. So you can shift the linearization, or you can add a general element as a constant to the moment map and get rid of singularities that way. But you can also do this blow up construction, and and then obviously, I mean, if your group is semi-simple, then you don't get the chance to use the torus point of view. So all you can do essentially is blow up construction, and this non-reductive setting, again with unipotent groups, they don't have any non-trivial characters, so you're sort of forced to do blow-ups. But I mean, I talked a little bit to Kenji after his talk, but I don't really know enough about the details of, but certainly the extended moduli space. So Lisa Jeffries' extended moduli space, he's using describing the representation, the moduli space, whatever, as a quotient of that is can be very useful from lots of different points of view. And yes, that's not really an answer to your question, but anyway.
Are there more questions? I decided that algebra me should rather shut up. Okay.
Well,
thank you very much.
Yes.